Welcome to Summarize Science, where we break down cutting-edge research. Today, we're looking at a new way to model one of the biggest challenges in fusion energy, plasma turbulence. This research focuses on the Wendelstein 7X, a massive and complex experimental fusion device called a stellarator. The goal of fusion is to contain plasma hotter than the sun, but this plasma is unruly. Like boiling water, it develops turbulence, which allows precious heat to escape and can stop the fusion reaction in its tracks. Understanding this turbulence is key, but the most accurate computer simulations are incredibly slow and expensive. This is where the researchers' work comes in. They aim to create reduced models, which are simplified formulas that can predict the heat loss from turbulence much faster. The model they built predicts heat flux based on three key plasma properties: the temperature gradient, the density gradient, and the ratio of electron to ion temperature. To build these models, they used a smart machine learning strategy called active learning. Instead of just feeding the AI a massive, random dataset, the active learning process allows the model to identify the areas where its predictions are most uncertain. It then specifically requests new, high-fidelity simulation data for those most informative points, making the learning process incredibly efficient. The team first built individual models for 7 different radial slices of the plasma inside the W7X. The results were impressive. As you can see in these plots, the model's deterministic predictions line up extremely well with the reference simulation data used for validation. This shows the models are not just memorizing the training data, but can accurately generalize to new, unseen conditions. Crucially, they didn't just get a single answer. They used a technique called bootstrapping to generate 95% prediction intervals. These shaded orange bands show the model's own uncertainty, which is essential for scientists to trust its predictions in the real world. But they didn't stop there. They also investigated creating generalized models that could work at any location, not just the 7 they started with. They tried 2 different approaches to achieve this. The first approach involved creating a formula to predict the model coefficients themselves, based on the radial position. The second was a single, generic model trained on data from all locations. They found the first approach, which adapts its coefficients based on location, offered superior and more robust predictions across new, untested positions. So, let's recap the key takeaways from this work. The researchers successfully used an efficient, active learning approach to build fast and accurate models for electron-scale turbulence in a stellarator. These models not only make robust predictions, but also quantify their own uncertainty, which is a critical step for practical use. This achievement is a big deal because these fast models can accelerate fusion research significantly. Scientists can now perform parameter scans and design optimizations that were previously impractical due to the high computational cost. Ultimately, this work helps pave the way for designing better, more efficient fusion power plants, bringing the dream of clean, limitless energy a little closer to reality.